Hey guys, what's up? It's Alex over at Laser Everything, and today we are going to be taking a close look at the Kaiweets KM601 multimeter and all of the different ways that we can use multimeters to test out various issues that we might be having with our power supplies. We're going to go over checking continuity, checking voltages that are going from the power supplies to the different components, and how to use the non-contact voltage feature that some multimeters have. If you're curious on how to diagnose potential issues with your power supplies, this is the episode for you. I'm going to walk you through exactly how I do it, step by step, so don't go anywhere because we're getting started right now. Are you guys ready to start messing around inside of your machines with all of these dangerous electronics? Another pre-episode disclaimer here, guys. Working on the inside of this equipment, especially while it's powered, is extremely dangerous. This video is for educational purposes only. I'm not an expert electrician or an expert on safely executing any of the tasks that you see in this video, and you should definitely consult a professional before attempting anything that you see me do over the course of this episode. For all of the tasks we're going to complete in this video, we're going to need a solid multimeter. A multimeter is a tool that will allow you to see how your machine is wired and check the voltage of the electricity running through the wires. A lot of you may already have multimeters, but for those of you who don't, we're going to take a quick look at the Kaiweets KM601 and some of its basic functions. If you already have a multimeter and you know how to use it, you can skip to the next chapter of this video. I needed a good multimeter for this video, and luckily Kaiweets was kind enough to send this one over for me to check out. If we open the box here, it actually comes with a really nice case, as well as a detailed instruction manual that's complete and easy to read. Let's take a look inside the carrying case. It includes two sets of AAA batteries, some standard probes, these are what we'll use to get measurements from our electronics, and it even comes with a thermometer you can use to gauge temperature. Last but not least, we have the actual multimeter, which fits right into its own case pocket. The front face of the device is pretty straightforward with a nice big screen and all the buttons you'll need to operate its main functions. On the left side, we have the button that activates the built-in flashlight. On the back, we have a nice textured grip case and the flash module. On the right side, we have the button to activate the auto power off function to help you save battery. And up top, we have the main power button, as well as the sensor for the non-contact voltage detector, which we'll touch on later. The bottom has sockets for our 4 probe connectors. This is where we'll plug the probes in. The case is on there nice and tight, so it definitely isn't going to slip out. If we wrestle it off, we'll get access to the battery compartment in the back. The case is flexible but thick and definitely durable. The battery compartment is held in place with one small Phillips head screw. It doesn't come with any extra screws, so don't lose it. If we take off the back, we'll find the meter takes 3 AAA batteries, which come included. It's heavy, and all of the components feel really high quality. Let's turn it on and navigate some of the basic functions we'll use during the course of this video. The unit powers on into auto mode, which is great for jumping right into basic tasks like testing resistance and voltage. Once it's on, we can test out that flashlight, which is super handy when you're working in dark or confined spaces. While auto mode is great, I prefer to select the specific mode I want to use. We'll do this with the large function button in the center, which will cycle through the multimeter's various modes. The first mode we'll be using in this video is called continuity, which checks to see if 2 points in a circuit are connected. This will come in handy when making sure our system is grounded properly. When selecting any mode on the multimeter, the correct probe ports to use will flash for a few seconds, so you're sure you're using the correct ones. For continuity, we'll need to use the voltage and COM, or common ports. Typically, your red probe will go into the voltage port and your black probe into the common. But the probes are identical, so if you mix them up here, it's not a huge deal. To test the continuity function, we simply have to touch the 2 probes together, completing the circuit. If we have a strong connection between the 2 points, the continuity value will read 0 or as close to 0 as possible. What we don't want to see is OL, which stands for open lead and means we have a break in our connection. A A value of 0.1 or less would be acceptable, but you'll usually see the 0 we're looking for. The second mode we'll be using today is our voltage mode. This mode tells us the difference in voltage between 2 points, which is extremely useful for detecting issues with our power supplies. If the power supply is not outputting the proper voltage, our components won't work as expected, which is a huge problem for a lot of people, especially with inexpensive Chinese power supplies. For this test, we'll be using the same voltage and common port on our multimeter, just like we did for continuity. The test itself is very simple. Grab a double or AAA battery and hold each probe to one end of the battery. Since the battery is so low voltage, this is safe, but we do not want to touch the contacts on our power supplies when working inside the machine later. This AAA battery outputs 1.6 volts, which is confirmed by the reading on the multimeter. That's all there is to it. The final mode we'll check out today is called the non-contact voltage detector, or NCV. The non-contact voltage detector does exactly what it says. It detects voltage running through our system without actually having to make physical contact with any of the wires. This is a simple and safe way to determine if the wires we are working with pose a hazard to us. First thing we'll do is switch to the NCV mode on our multimeter. This mode does not utilize the probes, only the sensor at the top, which we identified earlier in the video. To test this mode, I have the power supply brick for my video camera. When the power supply is a sufficient distance away, the NCV will not be triggered. As we bring the sensor closer to the power supply, we can see it begins to detect a low voltage. As the sensor nearly comes in contact with the wiring in the power supply, it can now detect a high voltage running through the circuit. The NCV is a handy feature that can help you determine if your system is safe to interact with, but do not rely on it exclusively. Always disconnect your machine from the wall and wait for the capacitors to discharge before beginning work. Now that we understand multimeters, how they work, and which functions we'll be using for our tests, let's take a brief tour around the inside of our galvo machine and identify the parts so we know what we're working with before we begin. Most modern galvo laser cases are held together by screws on the front and back plates. Removing them should allow you to remove the top and slide out the side panels, obscuring the components inside. For now, disconnect the power from your machine to reduce the risk of electric shock during disassembly. Take a moment to open your case before proceeding. There's a lot going on here, and it can be a bit overwhelming, but if we break down the individual components, it actually makes a lot of sense. On the bottom left, we'll see our power port, where our red line, blue neutral, and yellow ground wires enter the system from the wall. Above that, we have our stepper driver. This device is what controls our extension axis stepper motors, like our rotary devices. Not all lasers have internal stepper drivers, so you may not have this part. To the right of that, we have our laser controller that controls the entire system. This laser controller is the BJ JCZ EasyCAD Lightboard. Next, we have our EMI filter. EMI filters clean the power coming into our system so our components can use it. Exercise caution around these. Its line and neutral contacts can be the most exposed inside the entire machine. I gave myself quite a jolt making this episode because I brushed a little too close to them while moving some wires out of the way. Always make sure to use one hand at a time when manipulating components and wires inside the machine. That way, if you get a shock, it will not run in one hand and out the other, potentially crossing your heart. The last components on this side are our power supply units. Each power supply unit has a red line, blue neutral, and yellow ground wire powering the unit from the wall. They also feature the voltage terminals where the outgoing power is sent to the various components in our machine. Typically, these are composed of red positive terminals and black negative or common terminals. These will be important when we begin our testing. If we turn the machine around so we can see the other side, we'll notice the large laser source. This box is the component that actually generates the laser used for engraving. Never open your source. Not only will it typically void any warranty you have, but its internals are also highly sensitive and are very easy to damage. The yellow cable here, though yours may be a different color, is your fiber optic cable that carries the laser to the galvo head. It's very important to never bend this cable. Fiber optic cables are typically made of glass and easy to break. Excess fiber optic cabling should be distributed in a large loop as pictured, rather than a tight coil. Fiber optics that are coiled tightly wear much quicker than those with larger bends. If your fiber optic cable is wound in a tight coil, you can carefully remove the zip ties keeping it coiled and spread the cable out over a wider area, avoiding tight turns. Finally, my system has one tiny little 12-volt power supply that used to be connected to my EasyCAD 3 board. I don't use this one anymore, as I downgraded this machine to an EasyCAD 2 board, so we'll be ignoring it for this video. The first test we'll run against our machine is the continuity test for ground. If you don't know what that means, it's much simpler than it sounds. Essentially, we don't want our electronics or our bodies to get hurt if electricity is leaking out of a component and into the case or other components. The ground wire gives the electricity a safe path out of the machine and away from us. On typical US plugs, the third large prong is the ground wire. Depending on your country, you may not have a ground wire built into your machine's plug. If that's the case, you also have a secondary grounding point on your machine, which you can use to run copper wire into a stake that will be driven into the literal ground. Grounding manually like this is difficult and must be done in a very specific way. It's out of the scope of this video, but if you're curious about it, a quick Google search will turn up lots of information on the topic. Before starting this section, it's vital you unplug your machine from the power. The continuity testing feature of your multimeter is not designed to handle voltage, and you can damage your machine or multimeter by performing these tests with your machine plugged in. The goal of the continuity test is to ensure that there is an uninterrupted path between the machine case, the casing of components, and the ground wire's exit point in the machine. To find the exit point, we'll take a look at the inside of the back of the machine, where we plug it into the wall. On the back of this connector, we will find a blue neutral wire, the red line wire, and the yellow ground wire. Looking at the reverse side, it's easy to tell which of the prongs connects to the ground wire. Once the electricity has reached this point, we can assume it has safely left the machine to ground, so this will be our primary testing point. For all of our continuity testing, we will hold the red probe here, as this is the point on the machine that all case surfaces and component casings should have an uninterrupted connection with. If your power port doesn't have a ground prong, you'll test on the casing ground connector instead. Once our red probe is settled, testing for continuity is extremely easy. Since my PSU case is grounded to the chassis, we'll be probing the machine case and component casings. Note that your mileage may vary, and your power supplies may not be case grounded. If your components are mounted to an insulator like a plastic frame, you'll want to check the ground wires on each terminal instead. With the red probe on the ground pin of the power connector, simply test various surfaces, or ground terminals if needed, inside your machine. We're looking for our multimeter to return a reading of 0, indicating that the tested surface is grounded. Grounding is important because if there is a short somewhere in our machine, we don't want to touch the case or component and get shocked as a result. If your front panel is not making contact with the rest of the machine chassis, it will likely not return a 0 in your continuity test. Touching the front panel to the body of the machine should resolve this, as they're not always grounded with wire. Before continuing on to the voltage section of the video, we should first cover the basic anatomy of our power supplies. We will always have 3 terminals labeled line, neutral, and ground. The line and neutral terminals are where the power supply receives power from the wall in the form of AC or alternating current. The other terminals will be our output terminals, which will supply their assigned voltage as DC or direct current. There will typically be positive and negative output terminals. Sometimes instead of a negative output terminal, you'll see it listed as COM or common. For the purposes of this video, negative voltage output terminals and common output terminals can be considered the same. Do not confuse these output terminals with the line and neutral input terminals. The line and neutral terminals should only ever be tested for voltage in AC mode on your multimeter. The positive and negative output terminals should only ever be tested for voltage in DC mode. It's important that you do not cross the probes from the AC side of the power supply to the DC side of the power supply. For this section of the tutorial, we will be completely ignoring the yellow ground terminal. To switch between DC and AC on the KM601 multimeter, we will hit the select button while in voltage mode. Other multimeters may have AC voltage and DC voltage as completely separate modes. With our continuity tests complete, you may now plug your machine back into the wall. Exercise extreme caution from here on out, as there are likely multiple points inside your machine which will deliver an electric shock if you touch them while energized. Testing the voltage being demanded by our power supplies will tell us two very important things. First, we will be able to determine which laser components are being powered by which power supply. We can achieve this by matching voltage demand from the component with the voltage supply from the PSU. Second, we will be able to diagnose issues with our power supply if we determine they are not supplying the power for which they are rated and for which the components required to operate properly. The first thing we need to know is what voltages our various components require. If we take a look at our laser source manual, we can see it requires 48 volts of power. The galvo head specs call for 15 volts, and the EasyCAD 2 controller manual states it requires 5 volts. Researching the voltages required by various components can take a while. If you have any questions, you can always start by looking for a model number and Googling it, asking for help in the Discord server or Facebook group, or reaching out to your machine manufacturer. Having completed this list, we can start to test our power supplies to identify them and make sure they're putting out the correct voltage. We'll begin by testing the power supply on the far right. It lists an output of 48 volts at 7.3 amps, so this should be the unit supplying power to our laser source. When testing, we want to place the red voltage probe on one of the 48 volt terminals and the black common probe on one of the negative voltage terminals. If the power supply is functioning correctly, we should get a reading of 48 volts. If for some reason you probe the terminals backwards or connect your probes to the multimeter backwards, you may see a negative voltage instead, such as negative 48 volts in this instance. Don't worry, that result is still perfectly valid. So we found our 48 volt power supply for our laser source. The process is exactly the same for the remaining power supplies inside our case. The next unit we'll test should be the 15 volt power supply for our galvo head. And we're getting a reading of 15 volts, so that one is good to go. Next, we'll test the 24 volt power supply for our stepper driver. This one checks out as well, as we get a reading of 24 volts from the PSU. Finally, we can make sure our 5 volt terminal delivers 5 volts, and it does. So we now know that we're getting good voltage from all of the power supply units in our case. The last thing we can check is the voltage going into our power supply. If our power supply is not functioning correctly, it may not be receiving the proper voltage from the wall outlet. Like we mentioned earlier, we must only test the input side of the power supply with the AC voltage setting, so we'll switch to AC mode quickly on our multimeter. Once that's done, we can touch the red voltage probe to the line wire and the black common probe to the blue neutral wire to get a reading. Here in the US, we're expecting 120 volts from the wall, and that's what we're reading here. So again, we should be good to go. Under no circumstance do I recommend ever trying to fix a power supply on your own. They're extremely inexpensive and common, so they're easy to replace. If you discover one of your power supplies is having an issue, simply order a replacement from a trusted company like Meanwell and swap out the unit for a new one. This is the safest and easiest option without exposing yourself to unnecessary risk. If you don't know where to get genuine power supplies, check out the links down in the description and shop wisely. There are many fakes out there that can be shoddy and dangerous. Don't put yourself at risk to save $5 to $10 on a power supply. And that's about it for today's episode, guys. I know there was a ton of information jam-packed into this episode, guys, so if you're confused or need help, definitely check out the absolutely free Facebook group or Discord server, both linked down in the description for you. I really hope that you guys can walk away from this episode feeling a little more familiar with the internals of your machines and maybe even ready to tackle some issues that may come up in the future with your power supplies. So if you got value out of this one, guys, don't forget to smash the like button, let everybody else know the content is good, and don't forget to subscribe and hit the notification bell so that you get notified the next time I upload a video. If you guys love the channel and it's the best thing that ever happened to you, don't forget to check out the Laser Master Academy. It's the #1 way to support the channel, and it allows us to continue putting out all of this content for free for everybody week after week. So go Go and check it out. It starts at $8 a month, and every single new member that we get makes a massive difference. You get a ton of bonus goodies for signing up, like our laser parameter libraries, bonus episodes of the podcast, and live streams, and a whole lot more. So go check it out over at masters.lasereverything.net. And I think that's all I've got for this one, guys. Thank you so much for watching this episode. Please be safe out there while you're messing around with your machines, and I will see you in the next one.